In our previous video, we kind of introduced thermodynamics or thermochemistry, and we introduced quite a few terms. And we talked a lot about heat flow and how you can think of thermodynamics, thermochemistry as the study of heat flow. So we're going to look at another really important key term. This key term is heat capacity / specific heat. Heat capacity is the amount of energy required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius. Now, when you're talking about a heat capacity for a certain substance, you refer to it as a specific heat capacity because the heat capacity of each substance is different or specific to that substance. So these terms can sort of be used interchangeably, heat capacity, specific heat. And what you'll see at this part here to the bottom left is a chart that has different specific heat values. And there's quite a few substances on here. The two substances that I'm going to focus on are just some common ones. So we have iron and water, or H2O. You can see that iron's specific heat is a pretty small number. So just to make this number a little bit larger here so you guys can see, it's 0.45. Now the value for specific heat of H2O is 4.18. Now if you think about this, and just some things you've seen in everyday life, if you have a piece of metal outside in the sun all day, it's going to get really warm pretty quickly. And vice versa, if you had a bucket of water out in the sun, it's going to heat up, but not nearly as fast as a metal. And this can be seen in their specific heats. So metal, such as iron, a metal such as iron, has a specific heat of 0.45, less than 1. So it doesn't take much energy to heat up metals. So iron will heat up pretty quickly with not a lot of energy. So remember, its specific heat describes basically how much energy it takes to heat up the substance. So it's a small number. Water, on the other hand, is really good at absorbing energy without changing its temperature that much. So it takes a lot of energy to heat up water. So its value is much, much higher than the metal. So again, if I had these two substances out in the sun, and let's say I let them sit out for, I don't know, let's say like 30 minutes outside in the sun, and I had, let's say, 200 grams of iron and 200 grams of water, and I set them both out in the sun, I would expect the iron to get much warmer than the water, because if they're absorbing the same amount of sunlight, the same amount of energy, the water is going to heat up much less than the iron in the sun. Now there's an equation you can use for this, and this equation is Q equals mc delta T. What I have highlighted here is just what the different variables stand for. So Q represents the heat, or the heat flowing in or out of whatever substance you're looking at. And this will be measured in a unit called joules, which is represented by a capital J. M stands for mass, and in this case it's represented in grams. It can be in kilograms. We'll kind of talk about that maybe in later videos, but for this video we're going to focus on this being in grams. And a capital C or a lowercase c, depending on where you find your information from, what textbook you look at or what online source. Sometimes they use a capital C, sometimes a lowercase c. Sometimes it will have this subscript s, other times it won't, but it'll almost always be a letter C. Stands for the specific heat, and the unit for specific heat is going to be joules divided by grams times degrees Celsius. You might also see this as kilojoules divided by kilograms times Kelvin. You can see a lot of different varieties. Basically what you need to realize when you look at a problem like this, if you use a Q value, let's say you decide that your unit, your C value for your specific heat, let's say you look at a data table, and the data table actually gives you a unit for your specific heat that's kilojoules divided by kilograms times Kelvin. If this is the case, it's not a huge deal. It's just you need to realize that if you're using a specific heat value that has this unit on it, that means that your mass is going to have to be in kilograms, and your Q is going to have to be in kilojoules, and your T is going to be in Kelvin. So you just have to be careful and make sure the units play well with each other, that they're in agreement. But the problem we're going to look at is going to be a pretty basic one, and it'll be this sort of setup here. Normally what's going to happen, you might be given the mass, this was specific heat, and the temperature change, and you'll be solving for Q. Or you could be given any of the three variables and you'll have to solve for the fourth variable. That's normally what you'll see at this sort of foundational level in these questions. So this could be really useful because if you can measure the heat flow, if you can measure Q, you know the mass of the substance, and you know the temperature change, then you can actually identify the substance by solving for C. Remember, C is specific heat. So this is a specific value that is special for every substance. So let's say I had a situation where I had a chunk of metal and I wasn't quite sure what it was. Well, if I can measure Q, M, and delta T and solve for specific heat, and I have a reference chart, maybe I find online or in a textbook, and I see that when I solve for C the value is 0.9, well, I can be pretty certain that I'm dealing with a piece of aluminum, which is what you can see up here in the table. So it's really a interesting kind of calculation you can do to solve like the identity of a mystery element. So let's just take a look at sort of a basic question here. So this is a pretty simple one. And it's just asking how much heat is required to raise the temperature of 200 grams of H2O or water by 4 degrees Celsius. So we're just going to use the formula that we just learned. Q equals mc delta T. Now, one thing I really like to do with problems like this is just to kind of take inventory of what I have and what I do not have. So I'll just kind of make notes of the 4 variables I'm dealing with. Now the question asks how much heat. So I don't know what Q is. That's the whole point of the problem, is solving for Q. Now I should have the other 3. So let's look. 200 grams, that's a mass. And I do not see a specific heat, and we'll talk about why that is in a second. But I do see that the temperature is increased. So I'm raising the temperature to 4 degrees Celsius. So my delta T, and I should have mentioned this earlier, but delta, the Greek letter delta in science almost always means change in. So when you see delta T, that means the change in temperature. I don't technically know the final temperature in this problem or the initial temperature of this water, but I do know it changed by 4. So I can just plug in 4 degrees Celsius for my delta T. What was the change in temperature? It was 4. This problem tells me it's 4. Now you might encounter a problem where they tell you something like the temperature at the beginning was like, let's say 20, and then it changed to 24. Well, that would also be a delta T of 4. So don't freak out if they give you 2 temperatures. If they tell you the temperature was something at the beginning and it was raised to something at the end, just take the final temperature minus the initial temperature, and boom, you'll have the delta T. So it just is an extra step, but it's not, it doesn't necessarily make the problem any harder. In this case, they just said, hey, guess what? The temperature went up by 4. Now, I don't have the C value here, the specific heat, and there's a reason for that. This is water, and this is just a specific heat value you're going to have to get very comfortable with. And if we look back at the problem, the previous page, we can see the specific heat here of 4.18. Sometimes that value will be given to you in the problem when it involves water, and other times it's just a value that is assumed that you know. So it would be a good idea just to kind of jot down what that value is. So for water, the specific heat is 4.18. And this is by far the specific heat number that you're going to be using the most in these types of problems. Water is going to be used quite a bit. So how do I solve this? Well, it's just going to be a simple algebra problem. I'll take Q and set it equal to 200, which is the mass, times the specific heat, which is 4.18, times delta T, which is 4. So I need to take the product of these 3 numbers. So it's a pretty simple question, actually. So we'll just simply multiply these numbers together. And just kind of a fair warning, you could see the specific heat value given to you in 3 decimal places, so keep that in mind. If you see a slightly different value for C than I'm giving you, that's very possible if you use a specific heat that goes to 3 decimal places. So we solve for Q. Q equals 3,344. So a question might be, okay, that's great, what unit is it in? Well, the unit that it is in is going to be the unit that you used for C. The unit for C is going to be based on the units of M and delta T. So the unit of C that we actually used in this problem, I didn't write it in the table, but let's go ahead and so we'll add that in. That was going to be, or that was, joules per gram times degree Celsius. And you might be wondering why the value for C has this really weird unit of measurement. Well, it's actually pretty simple. All you have to do is rearrange this equation and put C by itself on one side. So if you were to shift C to the left side, let's say, of the equation by itself, or to one side of the equation by itself, it would basically be C equals Q divided by M times delta T. So that's why this unit is what it is. It's the unit for Q divided by the unit for M times the unit for delta T. So it's joules per gram times degrees Celsius. And that's basically because if you manipulate the original formula and solve for C, you get Q over M times delta T. So what's the unit we use for Q? Well, it's the same unit for Q that was used in your specific heat value. So we use joules, so Q comes out in joules. So what did this problem tell us? Well, if you want to take 200 grams of water and you need to raise its temperature by 4 degrees Celsius, you're going to have to supply 3,344 joules of heat. So again, this is just kind of a basic example. In future videos, we'll look at something a little bit more complicated, but this gives you a pretty good foundational understanding of specific heat and how it could be applied.